Hey class, it's Mr. Hofstad here, and let's get right to it, continuing on with our topic 5, focus on electricity. Today, or part of today, will be focused on electron drift speed. So what's important to know here is that electrons are always moving randomly, right? They're always bouncing around. Think of electrons as these tiny little subatomic particles that are a little bit jittery, a little bit all over the place, constantly jumping around, especially inside of a conductor. So they're actually moving around quite fast. This is 1,570 kilometers per second, which is getting pretty close to the speed of light. And just if you want to know what that number really is, it's their Fermi velocity, as it was discovered by the scientist Fermi. Pretty sure he's Italian. Don't know 100% though. You can look into him if you're curious. So these electrons are constantly moving, but they're moving randomly. So they're just as likely to move left as right, as up as down, as diagonal. There's no reason or rhyme to their movement if there is no applied electric field. There's just this zero net movement, was what we would call it in our nice physics term. So overall, the electrons are averaged out to be in the same position throughout the whole time. That's happening when there's no external electric field applied to it. What happens is when we start to add in an electric field, there still is the random movement, but we're giving them a little bit more direction, and that net speed or net motion is the electron's drift speed. So that'll be the average speed that a particle, which we're mostly going to be looking at electrons, if not always looking at electrons. So it's the average speed that it attains due to the electric field that's applied to it. So an electron will still be rattling around, as you can see in this image down at the bottom of the screen, randomly up and down and all around. But now that we have an external field applied, there is this net motion to the right, right? So this would mean that we have a positive plate or a positive side of the field here, sorry, a negative and a positive on the right side, where the negative charges are being attracted to that positive side. And they're still moving around at their Fermi velocity, 1,570 kilometers per second, but the random motion now has this small net velocity in the direction of that applied magnetic or electric field. All right, so here's a nice image. The arrows are of this electron bouncing around randomly, but if you add up all of these velocity vectors, all these arrows are their velocity vectors at different points in time, the net, or the sum of all of those velocities, will be slightly to the right. And that's because we have an electron moving towards the positive side of our field, because the opposites, of course, attract. The electrons are being repelled by this negative side and being attracted towards this positive side. So the electric field here is drawn in with these red arrows. Just a quick recap, or a quick reminder from that last lesson. And what you'll focus on in Physics 30 is the electric field's direction is determined by a positive test charge placed in the field. So if we were to drop in a positive test charge right here, why are you not giving me? Right, a positive guy here is going to be repelled from the positive towards the negative, so the electric field is in this direction. But an electron is negative, and it's going to travel in the opposite direction of that positive test charge. So that's what's really going on. There's our net velocity, which we call our electron drift speed. All right, how do we calculate it? This is what we're all here for. This is why we love the physics, the math, and the formulas, right? The drift speed, which is v, same variable that we used in physics 20 for speed, can be calculated using I, which is current. So current will always be charge per second, or coulombs per second. I guess the IB like to write it with the -1 exponent. Coulombs per second is your charge. It's going to be equal to the density of electrons, right? So the charge carrier density. Charge carrier, for all the questions we're going to be working with, is our electron. So this unit, I don't like, I'm going to call it electrons per meter cubed, or how many electrons you have per unit of volume. Right, so we could have 10,000 electrons per meter cubed. We could have 10 billion electrons per meter cubed. That will be our N value, the density of our electrons, or of our charge carriers. A is our area. We're usually working with wires that are cylindrical, so the cross section of a cylinder will be a circle. So we'll usually be using our pi r squared, pi times radius squared, remembering that radius is half of the diameter, so it could be pi, that's a weird pi, sorry, pi times our diameter over 2 squared. And our drift speed will be in meters per second, right? That one's pretty straightforward. It's just like any other speed. And Q is our charge in coulombs. So pay close attention to those units. You'll see that they all cancel, or all equal out. So we have coulombs times seconds to the -1 on the left. Here we have number of electrons per meter cube times meter squared. So we're canceling out all of our meters but 1. So then we have meters per second, so we cancel out our last meter, and we have electrons per second, and then we're getting coulombs. This is really coulombs per electron, or per charge carrier. Right, that's the charge on an individual carrier, on one carrier, which is given in our data sheet. For an electron, we have 1.6 times 10 to the -19 coulombs per electron. Yes, 1.6. So that's the number you're going to be working with the most, because we're working with electrons the most. 1.6 times 10 to the -19. That's our, oh, that's supposed to be a 9. Oops, -19 coulombs per electron. You won't always see electrons given in formulas like this. I'm just showing you, trying to explain this charge carrier density and this charge on carrier differently, where the electron is our carrier. You could use conventional current, and then it would be a positive charge, but that's not as standard. More often you'll see, and with the homework questions, it'll be electron more often. All right, where does this fancy formula come from? We can derive it using this cylindrical wire, which is what we're going to be working with most often. And current in amps is the electric charge flowing past a certain point per second. So if we're at X and we're just timing how many charges, we're counting how many charges will go past per second, right? Almost think of it like a river, and you've got these little, I don't know what you'd think. Maybe since it's warming up here and the North Saskatchewan is starting to melt a bit, you could think of these all as little ice flows, and you're going to be counting how many ice flows are going past your point per second. That would be really what current is, where the ice flows would be electrons. So we have to imagine all the electrons are moving at the same speed, right? That would be kind of related to our electron drift. They're all moving randomly, but their net velocity should be the same in this direction, the direction created by our electric field. So if we start our watch and let it run for a certain time t, which will be this guy up here. Sorry, I lost my pen. Here's our time t that we're counting how many are flowing by. So when we started, these were the first ones to pass by point X. As time goes, we're getting more and more of these electrons. The highlighted electron, which I'm thinking is this guy here, has traveled a distance L. So here's the distance that our super important electron has traveled, L. In fact, in the time t, all of the electrons of the cylinder of length L have flowed past you. So anything within this length of the cylinder has already flowed past me. This is just a derivation. This is showing you where this formula comes from. It's not the be-all and end-all as this formula is given in your data sheet. This is just some interesting background explaining the math. So we know all of those electrons inside of that cylinder have flowed past us, but we want to determine the current, right? So how many coulombs per second? First, we need to find out how much charge has passed point A. So the volume, in order to find how many of these charges, we need to find out how many electrons, because we know the charge per electron, but we need to count how many electrons are here. We're going to use the volume of the cylinder with the cross-sectional area of this. Here's our area A times the length of the cylinder, right? Length of the cylinder times its area gives us the volume. And once we know the volume, we can multiply the volume by the number of electrons per cubic meter, right? That's our carrier density, or the density of electrons in this specific type of material, right? So this N value will be different depending on what conductor or what material you're working with. So we could find the number of electrons by multiplying the number of electrons per unit volume, N, times our area times our length, which is a volume combined, right? So that would also be N times our volume. And then our meters cubed will cancel out, and we'll be left with the number of electrons. So the length of the cylinder is actually the speed times the time, right? Coming from the equals d over t, where d is actually the length that they've traveled. Rearrange this to solve for d, or in this case, the length. So the charge carried by electrons, we can replace this length with the time and the velocity, and Q here is the charge per electron. So this is just a different way of expressing our length, and now we want to find the actual charge rather than the number of electrons. So we'll take the same number of electrons in this cylinder, but now we're multiply by how many coulombs there are per electron. Coulombs per electron, which is our 1.6 times 10 to the negative 19 on our data sheet. So the amount of charge which passes point A in time t is calculated using n times cross-sectional area times drift speed times time times our charge per carrier. But now we want to find, instead of the charge, we want to find current, which is of course charge divided by time. So we can just kick this time out over to the other side and we get our current in coulombs, charge per second time, is equal to that density of electrons per volume times the cross-sectional area times our drift speed, and these guys will cancel out of course, and we get the charge per electron. So that's where the formula comes from. Here's an example. We have I here, current. We know the diameter, so we're going to need to use the diameter to find the area, but we're going to want to convert that to radius. And we know that we're getting an electron density of 8.5 times 10 to the 28. So pretty big number of electrons, but we're working with really big volume here. You're never going to actually have any wires that are on this scale. This would be kind of 3 meter sticks forming a cube. So rearrange our standard equation, I equals NAQV, to solve for V. I is 3 coulombs per second, N is 8.5 times 10 to the 38, and we're going to find the cross-sectional area of this wire using our pi r squared, so 3.14 pi, and r is our diameter divided by 2. That's going to be a common mistake if you're not careful, if you're just rushing through these questions. And we're going to multiply it by, since we're working with electrons, the charge per electron, which is our Q. 1.6 times 10 to the negative 19 coulombs per electron. And we get our speed, 2.8 times 10 to the negative 4 meters per second. So they're going pretty slow, but they're still going. Compare this with the Fermi velocity. There's not much of a comparison. Fermi velocity is 1.57 times 10 to the, what would it be, 6. Here we got 2.8 times 10 to the negative 4. We're an order of magnitude of 10 difference. So that's just important to note that the electrons are traveling a lot faster in their random Fermi motion than they ever will be traveling inside of a conductor with their net drift speed. All right, you have a homework assignment on this stuff. It should be a pretty quick one. I'll see if I can get you guys another video out by later today, but this is a good start anyways, and please let me know if you have any questions about electron drift. Hopefully it's nice and straightforward for you. Good luck. See you with 5.2 later.